To build a functional quantum computer, you need error correction. But right now, the industry standard, topological surface codes, requires a massive compromise. You have to dedicate thousands of physical ancilla qubits just to protect a single logical qubit from environmental noise. That geometric redundancy inherently limits performance. The sheer physical overhead traps current fault tolerance thresholds right around 1%. A recent paper by independent researcher Andrés Sebastián Pirolo proposes abandoning this geometric approach. Instead, the research outlines a system built on number-theoretic dynamics. Specifically, it takes the discrete mathematical operations of the 80-year-old Collatz conjecture and repurposes them into a functional error correction code. By shifting error correction into arithmetic logic rather than a physical grid, the research explores a model where stability isn't tied to spatial redundancy. This chart shows the result, a 2.0% fault tolerance threshold. The dashed gray line is the unprotected baseline, failing at 0.1% noise. Follow the solid teal line. The Collatz code protects logical fidelity out to 2%. That is a 20-fold improvement in stability, achieved entirely without adding a single physical ancilla qubit. To understand how those numbers are possible, we have to look under the hood and deconstruct exactly how a purely mathematical map functions as physical quantum logic. The first step in evaluating this threshold is mapping the standard Collatz rules onto a quantum state space. We visualize this using the block sphere diagram. At the North Pole, we define logical 0 as the positive attractor. Down at the South Pole, logical 1 is the negative error state. Environmental noise drives the central state factor down into this negative domain. To fix this, the system needs a specific mechanism, a trigger that initiates a unitary rotation to push that state vector back up to logical 0. Framing the Collatz map geometrically on a block sphere translates an abstract arithmetic problem into a solvable equation in quantum mechanics. Finding that recovery operator requires locating a bridge between the positive and negative numbers. This topological overlap graph maps forward computational trajectories for positive and negative integers. Their intersection reveals exactly 679 nodes existing in both domains, shown as this central cluster of gold bridge nodes. These nodes enable parity tunneling. If the system is trapped in a negative error state and hits one of these bridge nodes, it can execute a deliberate sign flip to tunnel back into the positive domain. The system treats these 679 integers as an order 1 hash map. It raises a syndrome flag simply by checking the absolute value of its current integer against that pre-calculated list. Using a simple arithmetic lookup process eliminates the need to build a secondary physical grid of ancilla qubits to detect errors. To test if parity tunneling actually works, the researchers ran a quantum walk algorithm to measure the stability of the negative C-5 error state. They executed a parameter sweep, systematically increasing the probability that a tunneling event would occur whenever a trajectory hit an overlap node. This graph shows escape probability versus tunneling. On the left, at low probabilities, the system remains trapped, but at the 0.003 threshold, a sharp phase transition occurs. The negative cycle collapses, resulting in a 100% escape rate. This confirms that the negative cycles are fragile structures. Because they possess zero topological depth against minimal quantum fluctuations, they are easily correctable. With the vulnerability of the error states confirmed, the final step was a stress test using the highly volatile seed state of 27, which takes over 100 computational steps to converge. During this test, continuous environmental noise was injected at every step, fighting the system's attempts to parity tunnel out of errors. The researchers tested two different correction regimes against this noise: a forced 100% deterministic sign flip upon hitting a bridge node versus a 50-50 probabilistic split. The results showed that the 50% partial correction strength yielded the optimal logical fidelity and maximum protection for the system. This mirrors weak measurement protocols in quantum physics, where initiating a partial collapse preserves the overall coherence of the system better than a heavy-handed full projective measurement. Achieving that 20-fold performance increase means relying on a hybrid classical quantum control logic, one that embraces statistical probability rather than trying to force a rigid outcome. Beyond theoretical physics simulations, this arithmetic protocol applies directly to high radiation environments like aerospace engineering. The current industry standard for protecting logic units from radiation-induced bit flips is triple modular redundancy. You have to build 3 identical processors and force them to vote on every single calculation to filter out errors. The Collatz architecture changes that hardware footprint. By hardwiring that 679-node overlap graph directly into the physical gates, a single arithmetic logic unit can flag and correct single-event upsets entirely internally. That internal arithmetic syndrome detection reduces total transistor count, cuts power consumption, and saves physical weight, all while maintaining mission-critical fault tolerance. Achieving quantum error correction relies on leveraging arithmetic structure instead of sprawling geometric space. Replacing an entire lattice of physical qubits with the Collatz map's topological bridges pushes stability thresholds out to 2%. The next research frontier is moving these Python-based Monte Carlo simulations onto dedicated stochastic computing processors that operate natively on these arithmetic structures. What started as an 80-year-old mathematical enigma has provided a viable blueprint for next-generation fault-tolerant computing.